Hello everyone and welcome to today's Explainer. I am absolutely thrilled to guide you through this topic. We are embarking on what I like to call the journey of the line, and we're going to completely demystify the Q data structure using the C programming language. Whether you've just started learning about data structures or you're an engineering student looking to brush up on memory allocation and pointers, you are in the perfect place. We're going to take this simple, universally understood concept of waiting in a line and we'll translate it directly into real, functioning C architecture. It's going to be a lot of fun.
Here is our quick roadmap for today. We're going to kick things off with Welcome to the Line, then explore core queue operations in C. After that, we'll contrast a stack versus queue, look at building queues, arrays versus links, explore types of queues, and finally wrap up with real-world queue applications.
Okay, let's dive right into Section 1, Welcome to the Line.
So, the absolute crucial point here is understanding the core principle of a queue, which is known as FIFO. F-I-F-O. That stands for first in, first out. A queue is simply a linear data structure that strictly follows this rule. The very first element that gets inserted into the structure is going to be the very first element that gets removed from it. It's a system built entirely around fairness and order of arrival.
Before we even touch the code, let's ground this technical concept in reality. Think about everyday examples. Like people standing in a ticket line, customers waiting their turn at a bank counter, or vehicles lined up at a toll booth. In all of these scenarios, the person or the car that arrives first is the one that gets served first. If you're person A and you arrive before person B, well, you leave before person B. It's totally intuitive, right? And this is exactly what we're going to teach the computer to do.
Let's move smoothly into Section 2, Core Queue Operations in C, where we translate that physical line into computer logic. So, how do we actually begin building this? We start with an initialization setup, typically called the init function. To create a completely empty queue, we set two markers, front and rear, and we set both of those to -1. In programming terms, setting these indices to -1 is literally our way of telling the system, hey, this line is completely empty, no one is waiting. Now we actually need data to join the line. We use an operation called enqueue. When we call enqueue 10 and then enqueue 20, we are inserting elements strictly at the rear. So our front marker points to our first arrival, the 10, and the rear marker moves back to point at the newest arrival, the 20. The line is officially forming.
But a line isn't much use if nobody ever gets served. That is where dequeue comes in. This command removes an element specifically from the front of the line. Going back to our bank counter example, this is the teller finally calling out, next in line. The 10 gets removed, and our front marker shifts over to the 20. First in, first out. It's working perfectly in code.
Beyond just adding and removing, we need to be able to check the status of our line without actually messing it up. We use utility functions for this. Is empty simply checks if that front marker is still -1. Is full checks if our rear marker has hit the absolute maximum capacity of our structure. And finally, peek is just a fantastic function. It lets us look at the front element, say that 20, without actually removing it from the queue. It's kind of like peeking to see who's next without officially calling them up.
Now, take a moment to appreciate the time complexity of these operations. When you map it out, it is O of 1 all the way down. This means big O of 1, or constant time. Whether your queue has 10 items or 10 million items, enqueuing, dequeuing, and peaking all take the exact same tiny fraction of a second. This incredible efficiency is precisely why queues are absolutely foundational in computer science.
Let's pivot slightly into Section 3, Stack versus Queue. If you've studied data structures before, you definitely know about stacks. A stack is LIFO, last in, first out. Think of a stack of dinner plates. You add to the top and you remove from the top, using only one end. But our queue, as we've learned, is FIFO. We enqueue at the rear and we dequeue at the front, actively utilizing two separate ends of the structure. It's a fundamental structural difference that completely changes how data flows through your program.
All right, let's wade into the deeper waters of C implementation in Section 4, Building Queues, Arrays versus Links. Now, what's really interesting about this concept is the trade-off we have to make.
First up, we have the static queue, implemented using an array. With a C-struct defining a fixed-size array, complete with our front and rear integer markers, this setup is incredibly fast and conceptually really simple to implement. However, it's totally rigid. If we define our max capacity as 5, well, this queue can only ever hold 5 items. It wastes memory if it's sitting empty, and it outright crashes if you try to squeeze a 6th item in there.
So, to solve that rigidity, We look at the dynamic queue using a linked list. Instead of a fixed block of memory, we define a struct node that contains our data and a pointer to the next node. Memory is actually allocated dynamically during runtime. When we end queue, we simply tell the system that the rear's next pointer equals our new node. The queue grows and shrinks precisely to match the data it actually holds. No wasted space.
To quickly summarize these engineering trade-offs, the static array queue gives you a really easy implementation but limits your size and lowers your memory efficiency. The dynamic linked list queue, on the other hand, requires a somewhat more moderate implementation using pointers, but it rewards you with highly efficient, flexible memory usage that grows on the fly. Choosing between them depends entirely on the specific needs of the software you're building.
Let's push forward into Section 5, Exploring Types of Queues.
Just as a quick baseline, everything we've talked about so far is a linear queue. It's the standard issue line. Insertion happens strictly at the rear, deletion happens strictly at the front. But as computing problems get more complex, this basic structure needs to elegantly evolve.
Enter the circular queue. Remember how static array queues can waste memory? Well, a circular queue solves this brilliantly. When the rear marker reaches the absolute end of the array, instead of just stopping and throwing an error, it connects back around to the very first position. It wraps around to reuse any empty spaces left behind by the dequeue operation. It literally turns a rigid line into a continuous loop of efficiency.
Then we have the priority queue, which actually breaks the strict FIFO rule, but for a very good reason. Think of a hospital emergency room. A priority 1 emergency patient absolutely must be seen before a priority 2 regular patient, regardless of who walked through the hospital doors first. In a priority queue, elements are served strictly according to their assigned priority level.
And for ultimate flexibility, we have the dequeue, which is short for double-ended queue. This is an advanced concept where you're no longer restricted to just the front and the rear. With a dequeue, both insertion and deletion are completely possible from both the left and the right ends simultaneously. It's a wildly versatile structure for specific, complex algorithms.
Finally, let's zoom out for Section 6, Real-World Queue Applications. We've looked at the micro-level C code, but where do these things actually live in the wild? The answer is literally everywhere. Right now, your device's operating system is using queues for CPU task scheduling. When you print a document, it enters a printer queue. Call centers use them to route customers in order. Even the internet runs on them. Network routers manage incoming data packets using strict queue scheduling. They even power advanced traversal algorithms like breadth-first search in complex graphs and trees.
I want to leave you with this final thought from our source material. Queues are one of the most important data structures in computer science and form the foundation of many real-world computing systems. It is absolutely amazing to realize that a concept as simple as waiting in a physical line secretly powers our entire digital infrastructure. So, the next time you're standing in line at the grocery store, I want you to ask yourself, where else in my digital life is a queue silently organizing the chaos right now? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.